Yeah. I think it's like back in now in the last minute.
All right, welcome to last ASTRODEBATA of this year. We're quite late, so no need to prolong introduction. Močnik is with us again. He was a student here, then he moved abroad. Is now for quite a while working in Hawaii. So we'll be hearing something about planets, I think.
Yeah. Well, good morning, everyone, and thank you all for joining us. It's a long way to get from Hawaii, turns out. It's actually really hard to get here when universities are in session. So 2 years ago, I gave you a promise, and I'm going to talk about this survey. It took 2 years to actually come when there's lectures going on here at this university. Okay, so one of the places that I visited after I left this faculty was being a postdoc at University of California in Riverside. And that's when we started this survey, TESS-Keck Survey, back in 2019. And then I moved to Keck Observatory, but I kept chipping in to this survey with as little research time as I had. There are cool results ever since 2022. There are many papers that we got out, and now we get to talk about them. So that's a pleasant way to work. Okay, if at any point you have any questions, feel free to ask as we go along or at the end as you like. Okay, let's dig in. So this is our team here in the middle of our survey architects, and we have two principal investigators. This is Professor Andrew Howard from Caltech, and this is Professor Stephen Kane from the University of California. And he used to be my advisor as a postdoc there. And this survey would not be made possible if it wasn't for a small army of really dedicated PhD students who did a lot of data reduction, a lot of paper writings. Hats off to them. So we were affiliated with these three institutions, University of California, Caltech, and University of Hawaii. And that's important because these three are the main institutions who are funding Keck telescope. So because we were from these institutions, we were able to get a lot of observing time from Keck. If we weren't affiliated with those, we wouldn't get such large observing time. And such survey would not be possible. Okay, so first I thought of briefly introducing, for those who might not be familiar with TESS, what it does and why that's important for us, and then our workflow and some of the cool stuff that we find within this TESS. TESS is a satellite. It goes around Earth every 2 weeks. It's a little bigger than the washing machine. It was launched in 2018. And the most important part are those 4 cameras at the top. So every camera is about as big as that. And every lens has a diameter of about 10 centimeters. You can imagine, like, there are 4 small telescopes on TESS. And they're designed to provide very high photometric precision, a very large field of view. That's the key of the TESS mission. Find as many planets around bright stars wherever they are on the sky. And to make that happen, it really needs a large field of view. So every camera takes like 24 times 24 degrees, and it's 4 of them. They're stacked on top of the other. And every sector is observed for 27 days. And once it's done, it goes on to the next sector and the next and so on. So after the first 2 years of the primary mission, that's the spec coverage, and you can see that there are some regions in the sky that got observed in multiple sectors. So you could end up with longer baselines and shorter, depending on how lucky you are where your target sits. So this is the first 2 years. But like I said, it was launched in 2018, and right now TESS is still observing. So right now we're in sector close to 90, like 86 or 87. So all of these gaps, not all of them, most of these gaps have now been covered in later sectors. Pretty much all sky was covered by TESS. And what it does is it measures flux of dozens of tens of thousands of stars. And it's hunting for these brightness dips in light curves of stars. And whenever it finds something periodic, something that looks like it could be a planet, then we find the planet candidate. So the planet goes into the star, it's well in the flux, and that's periodic. Then we say TESS found a planet candidate. And so far, there are over 7,000 TESS planet candidates. That's the blue curve. And we call them TESS object of interest. Now, these may or may not be planets. They may be false positives. They could be systematics, it could be stellar variability, it could be eclipsing binaries. But most of them actually are genuine planets. We just don't know which is which. And in order to confirm them, the red curve, that takes a lot of observing effort, a lot of follow-up, a lot of observing time with the biggest telescopes, most precise spectrographs in the world. And that is why not even 10% of those candidates have so far been confirmed, less than 600. And TESS-Keck Survey was targeting over 100 test planets. So a large chunk of that red curve actually came from the TESS-Keck Survey.
Why is there a large jump?
Large jump.
Yeah.
So at the beginning, TESS focused on bright targets, and then they implemented a pipeline to also look at fainter targets. So a bunch of these are much fainter than other targets. So that's the problem. And unfortunately, most of these faint ones are really, really difficult to follow up. People don't usually follow these up because it's observationally too expensive. So we focus on bright ones. But hey, they're there, and if you find 5 transiting planets, that's interesting. You will still follow up because it's, you know, cool. That's a good question. Thank you. I was thinking if I should even include this slide, problem just in case. So how do we measure a mass of a planet? How do we confirm them? We don't see planets directly in most cases, but what we do see is its host star. And that one goes around the barycenter. Sometimes the star is receding from us, like right now, and we measure a redshifted rate of velocity. Sometimes it's approaching to us, and it's a blue shifted rate of velocity. So we take these high precision spectra, we identify absorption lines, measure wavelengths, and from that, we know what the rate of velocity is. So this is the simplest possible scenario: a single planet around a single star in a circular orbit, and that's going to result in this nice sinusoidal function. But as you will see later on, it can be way more complicated than that, unfortunately. Okay, so this is where TESS-Keck Survey comes in. We do exactly what we just saw on the previous slide. And we do that with this telescope. This photo was taken from the summit of Mount Air, showing the seven telescopes. That's right here. But we use Keck. So Keck 2 and Keck 1 telescopes. And we use this one, Keck 1. That's the one that has a high-risk spectrograph installed in it. So we have a quick look inside Keck 1. You have this 10-meter diameter mirror. The light hits the mirror, it's reflected, it's the secondary, it's reflected, it's the tertiary, which is at a 45-degree angle. And now light goes here through the side ports and goes to the nascent platform, which has a thermal enclosure, and inside of that enclosure is a high-risk spectrum, which is splitting the light beam into a cross-dispersed spectrum. So that's the cartoon, but that's the actual example of a raw shell spectrum. So now we have to identify every single absorption line and measure the wavelength. So with enough of these spectrum, enough signal to noise, we can then identify planets. We can get down to 1 meter per second precision with iris. Okay, like I said, there were many work papers that came out. Every TKX paper has a Roman numeral. So if you Google TESS-Keck Survey 18, it's going to show up. And we absolutely have no time to talk about all of these, but I will focus on the first one. That's the survey design, target selection, what are our goals. And then this is the main result paper that published all the measured velocities of the masses. And then I'm going to briefly touch upon a couple others, just to give you a flavor of what other types of science we can do by simply measuring masses of planets. Okay, so TKS paper number 0. It defines our goals and our science themes, and it's 4 of them. This one is about measuring masses. If you know the mass and you know the radius from fast light curve, then you know the density. If you know the density, you can start explaining things like why is there a radius gap? And we're going to talk about that in a couple slides time, a couple slides later. Or what are correlations between stars and planets? All those cool things. System architectures, why the planets migrate, obliquities, all of these science cases require planets to have measured masses. And until now, we have a huge lack of those mass measurements of those types of planets that we, for the first time, went to observe them. And then atmospheres, which planets are great targets for atmospheric studies, how the planet system look like around the Volt stars, subgiants in particular. There are a couple of science options. Okay, like I said, 7,000 planet candidates. How do we choose? We have a generous amount of observing time, but still, we're still limited to about 100 targets or so, not more than that. So how do we choose the right ones? And the first step is, let's just weed out anything that looks obviously bad. And we follow this recipe. First, just simple things. Let's not observe anything very faint. Let's not observe anything that's not observable. Let's not observe anything that is an obvious binary star. And if it goes through, then we look, then we check at the light curves and see if light curves look like they're caused by transiting planets, or perhaps they're caused by eclipsing binaries. If they're eclipsing binaries, it's going to be V-shaped sometimes, but if it's a planet, it's going to be U-shaped. Are odd and even transits of equal depth? Do we have centroid offsets whenever a planet is in transit around? All of these are indicators that we're dealing with an eclipsing binary rather than a star. And with limited observing time, we don't want to burn our observing time on binary stars because we're interested in planets. So that's the first step. Then we take a high resolution image. Is it the host star is a single star, or is there another bright, relatively bright star right next to it within 2 arc seconds? If it is, well, that's going to contaminate our spectrum. Again, we're going to be burning observing time with something that's going to turn out to be very difficult to follow up on. So we want nice single stars, and most of them, thankfully, are single stars. We take a quick spectrum, we check if there's spectroscopic binaries. Are absorption lines double peaked? If they are, well, that's probably another star there. We don't want that. So if stars go through all of these vetting steps, then eventually they make it to the target list. And all that are good are marked in green, red ones are not good for one reason or another. Or they are already confirmed planets from earlier surveys, such as WASP or CALS, for example. But still, we have, this is just a small tiny subsection of all the targets that we met. And there's still way too many green planet candidates to look at. So which one do we actually want to choose for our science goals? And every science case had a ranked target list. And then from these ranked target lists, we had a very elaborate procedure with a pipeline that was picking up in a fair way all the different targets from different science cases, several iterations of them, to fit whatever we can within the allocated observing time. So keep adding targets, giving discounts to science cases if multiple science cases selected the same one to finally arrive to the final target set. So this was super quick, but just, that was needed to arrive at something that maximizes our science return within the allocated observing time. So those are the 4 science cases with large overlaps and these targets acceptable stars. Those are larger stars with larger planets. And typically larger planets are not as interesting for our other science cases. That's why the overlap here is smaller. But all the other science cases have a really nice, pleasant overlap. So one system can be analyzed by several teams and learn something new. Okay, that's a quick preview of targets that we selected. The y-axis are radar planets. And 10, this is about Jupiter size. So this is Earth radius, 10 Earth radius, that means Jupiter. And we only picked a couple of them, primarily for those evolved planet systems. But primarily, we focus on these smaller ones. So below 4 Earth radii planets. So planets that are smaller than about Neptune. Because those are the ones that are so significantly underrepresented so far. We know from Keck spacecraft that there's so many of them. Those are the most frequent planets that we know of, but we don't have mass measurements. So we needed something like TESS-Keck Survey to find and measure those large number of those smaller types of planets. So that's a distribution of our observing time. So every little line here is showing the target. And here on the x-axis is the number of radial velocity observations given to a certain target. And you can tell that we had our favorites. Some targets receive more attention than others, simply because some of them turn out to be really interesting. They have multiple planets in there, for example. And others turn out to be heavier and didn't need as many observations. And this last one was actually dropped. 300 observing events. 5,000 radial velocities, just with pirates, over 3 years of observing time span. And we supplemented that with our support telescope, automated planet finder, which is pretty much equally precise spectrograph, but it's mounted on a much smaller telescope. So this is 10 meters in diameter, and this is 2.5 meters or 2.4 meters, a lot smaller. So still great, but it only works for the few very brightest targets that we have. So the majority of the data, the most useful part of the data set we collected came from Keck. And that's why we call it TESS-Keck Survey. Okay, and this is our picture of all the measured masses, all the measured radii of our survey, marked in blue. And marked in gray are the planets that are available in the literature. And we can see there's so many hot Jupiters. Those are easiest to discover, easiest to measure masses, and it's already so many of them. We don't learn much from this parameter space. But we can learn a lot if we add a bunch of planets in this parameter space. And those were the ones that were difficult to measure. Because Kepler, even though it found so many planet candidates in this area, host stars were too faint to be followed up with ground-based telescopes. And now we have a bunch of them, all analyzed in a uniform way. And now we were able, for the first time, to remove some of these biases, publication biases, artificially reduced scatter in planet masses, for example. Anything that's lower mass, it didn't get to publication stage because planets were not significantly detected, for example. And now they are. So we were able to refine some of these mass radius relationships. So there are recipes out there that say, well, if you know the radius of your planet, you can estimate what is the mass of that planet. But those recipes were made a decade ago when there was hardly any planets in this area. So we were able to make them much more robust. That was the first easiest outcome that happened thanks to those mass measurements. Radius gap. Well, Kepler revealed, and our collaborator Benjamin Bolton discovered that there's lots of planets that are sub-Neptune and lots of planets that look like super-Earth, but there's a huge lack of planets in between, around radius of 1.7 or so. And why is that? Well, we didn't have any mass measurements for these, we just knew how big they are. And now we do have some mass measurements. And we can start speculating, why is it there's such a huge lack of planets in there? Is it because of photoevaporation, or is it pore-driven residual heat from the formation of planets? And there are several other theories proposed. And now with those mass measurements, we can tackle those things. We know what those planets are made of. And that's going to be the topic of one of the upcoming papers. But now we just have the mass measurements. We're going to try to figure out, at least provide some explanation of what it may be caused. Another feature is Neptunian deserts. So lots of planets here, lots of planets up there as well, with hot Jupiters, but very few planets in this area here, that line. There's very few Neptune-like planets or Earth radii with orbital periods of less than 5 days or so. Again, we don't know why it is, but it's a stark contrast. So in our sample, we intentionally selected, I think, 12 planets that firmly fall within that area, and we're gonna, with measured masses, we'll try to figure out what's happening with those planets. How are they different than the ones outside of this desert? Are they just transitioning from having large atmospheric envelopes to being bare rock? Are they actively losing stuff, or are the stars different? We'll see. Okay, another science theme is evolved planet systems. Oh, yeah, that looks green, that looks blue on my screen. So we allocated 16 observing nights to planets around subgiants. And with that, we roughly doubled the sample of planets with precisely measured masses around subgiant stars. And by doing so, we can now look at some of the statistics, the distribution of those planets, masses, radii, and we see that it so nicely firmly falls to wherever all the gray dots are. Gray dots are dwarf planet hosts. So there's no fundamental difference between subgiants and main sequence stars, which means that planetary system evolution does not significantly affect those nearby close-in planets. Those are just 10-day orbital periods, and they're not affected by the star evolving to subgiants. And we also discovered that about a fifth of those have outer gas giants, and that again is the same as main sequence stars. With 16 nights, we learned that planetary evolution does not significantly affect planets, at least with subgiants. Okay, atmospheres. So there is an equation that helps us estimate what's going to be signal-to-noise ratio for the planet that we want to look at around a particular star. And we see that the highest signal-to-noise of the atmosphere of a planet is for those that are largest, the smallest mass, hottest, and around smallest stars. And everyone's using this equation in exoplanet atmospheres. But the net result is that there's a huge publication bias now, because everyone is publishing bloated, fluffy planets around small, tiny M4 stars, and they're hot. But we don't hardly know anything about sun-like stars, and exoplanet atmospheres are all around sun-like stars, with the exception of our solar system. So our team tried to address that by identifying, I forgot, 13 or 12 exoplanet candidates, now confirmed, that orbit G-type stars, but they still have significant transmission spectroscopy matching. So easy atmospheric targets around G-type stars, hotter and bigger stars than we analyzed so far, and we have precise masses. And those masses are crucial for proper understanding of those atmospheric observations. And I should, I guess, first say that exoplanet atmospheres can be measured whenever they go in front of a star, because some of the sunlight is going to go through the length of an atmosphere of the planet. And by analyzing those spectra, you can learn what are the chemical compositions of those planets. Okay, this is our most interesting planetary system. TESS discovered 4 transiting exoplanets, and when we looked at light curves, we discovered 3 additional transiting planets, for a total of 7. It's crazy. And we managed to measure masses for 6 of them, planet B, C, D, E, F, G, but H, we did not manage to measure mass. Our precision was not big enough. We just placed another limit, which means that this is still not confirmed. This one is still a planet candidate, but we confirmed 6 of them in a radial velocity curve that looks as crazy as this. And you might notice that the amplitudes of those radial velocity curves are just a couple of meters per second, whereas this overall radial velocity curve is much bigger than that. This is hundreds. You probably can't read that, 150. So there was a lot more RV variability than just what's shown here. And that's because this star was also magnetically active. And that makes things more complicated. You need a lot more observing cadence, a lot better precision to deal with stellar variability and also be able to detect those planets. That's why you saw that was the target at the very top, with however many hundreds of observations. But it was so worth it. It's one of very few planet systems out there with so many planets. This is our solar system. TRAPPIST-1 and so on. That's the record folder with 8 planets, and we have 6 so far, plus one extra candidate. And what's so incredibly cool about it is that it also has a large transmission spectroscopy metric, which means that all of these planets in this planet system, not all of them, so planet H probably not, but others are easy to measure atmospheres. And by studying those atmospheres, you remove a bunch of variables, because all of these planets are the same age, they orbit the same type of star, and they form from the same protoplanetary disk, same composition. So whatever differences you will now find between planets C and D, for example, is going to be because of the distance from their host star, and a couple other parameters, but that's cool, right? And this is TRAPPIST-1. You've probably all heard about TRAPPIST-1 system, right? Rocky planets, habitable zone, yeah, let's pack suitcases and go there. But James Webb Space Telescope revealed that they're barren. There's nothing to breathe there. But this planet, probably they do have atmospheres. And unlike TRAPPIST-1, they're going to be a lot easier to measure. So this is now our primary target for atmospheric observations. But soon that's going to be coming out as well. And we're going to learn a bunch about these atmospheres. Okay, another interesting thing we can learn from looking at transits of planets is, are they aligned or misaligned with stellar rotation? So if you have a transiting planet, it will first start, in this case, the first case, it will start folding the blue shifted regions of the rotating surface of the star. And what that means is that the radial velocity curve through the transit is going to first get a redshifted bump. And then as the planet is transiting across the transit port of the star, it's going to start covering more and more of these redshifted portions, which means that the radial velocity curve is now going to be blue shifted. And in this case, this is the most common scenario in the universe. It's nicely aligned planet systems, including our own solar system. Planets go in the same direction where the star is rotating. But if it's asymmetric, that implies that the planet system is misaligned. Now, it goes in that direction, stellar rotation is this direction. And this effect, this radial velocity effect, is called Rossum-Lofgren effect. And the reason I bring this up is because one of our targets had this crazy misalignment. It's blue shifted first and then red shifted. And that's indicative of a retrograde orbit, which is unusual, but nothing too special about it. But what is crazy is that not only it's retrograde, but it's also going almost to the pole of the star. It's a polar retrograde misaligned orbit. That was weird. So how do you end up with such a crazy orbit? Well, incidentally, we discovered that there is an outer massive planet in the solar system, and if you put the physics together, you see that that outer planet can gravitationally affect the inner one, So then the ascending node of the inner planet is going to start to precess along the orbit of the outer one. So effectively, and in short time scales, short, couple millions of years. Don't see that from today to tomorrow, but if you observe again for 100,000 years, you will see that it's totally different now. In fact, it may not even transit anymore as a transfer. And what's funny is that it oscillates. It's terribly misaligned like now, and it goes to being totally aligned, it goes to being misaligned, and so on. And this is the best way to explain what's going on here and what's caused this planet to be so misaligned. It's only the fourth such planet system discovered so far, and all four of them have distant giant planets. So by discovering such cases, we learn how can planets end up in weird situations like this one. Okay. When the main paper came out, that's paper number 20, with all the mass measurements, there were several press releases going on. And one of them was published by Keck Observatory. So that's the picture that's been released. And it's showing all of our transiting planets for which we measured masses. And we can see that we focus on these sub-Neptunes heavy, and we also have a handful of rocky planets. And that's just a side product. But in addition to those 112, I think it is 112 transiting planets, we discovered an additional 14 non-transiting planets. Because when you're measuring masses of transiting planets, you can incidentally discover distant additional planets in the system, and they show up in radial velocity curves. So, in brief summary, we looked at 126 planets altogether. 112 were transiting, 14 were non-transiting. And I would say the most important bullet point is this one, saying 38 small planets with measured masses, and primary goal of the TESS mission was to measure precise masses for 50 such planets. So our survey alone almost already fully provided what TESS was designed for as a first goal of the mission. So that's the largest TESS follow-up survey in the Northern Hemisphere. 24 papers published, submitted, and there are more to come. We're going to submit another paper tomorrow on distant giants. Yeah, so that's pretty much it. At this point, I can let's stop here and invite you for questions. There's one more slide. Thank you.
Yeah, to calculate the mass of the planet from the radial velocity of the star, we have to assume the mass of the star, right? So what uncertainties are on this assumption of stellar masses?
They come from stellar evolution models,
Yeah.
and they are incorporated in those. That's the first step that you have to do. So
Yeah.
there are pipelines that we use. We put in stuff for the star,
Yeah.
and that spits out what's the mass of that star. That mass then goes in the second step, because now we know the ratio between planet and star, and we also know now the mass of the star, which comes from the model, and that uncertainty propagates further.
Yeah.
But uncertainties are small. We assume that we know the star, that it's a main sequence star, that there's no uncertainty, it's a giant sequence, so on. So there is some uncertainty, but it's measured in individual percentages.
Related question on the size mass plot. So the size of the circle is then the uncertainty.
Yeah, correct.
So on can you go back to the plot where you show masses versus planet sizes? This one, yes. So the circle size is the uncertainty?
Yeah, so in this case, it's larger circle represents more precise, so small circle is more uncertain.
Okay, so the
Bigger.
other way around.
Yeah. And some plots we made it that way. In that one.
So what's a typical uncertainty in this plot, like in terms of numbers?
So the best way to define uncertainty on masses is sigmas, number of. So if you measure mass of 6 Earth masses and your uncertainty is plus minus two Earth masses, then that's gonna be a 3 sigma detection. So for most of these, it's at least 3 sigma detection of mass. That means the mass measurement is 3 times as big as the uncertainty, as the lower limit of mass. But we do have some larger circles that are, I don't know, like 40 uncertainty, right? I mean, 40 significance on the mass measurement. Again, typically we expect large circles for large planets on Jupiter's. Those are easiest to measure masses. And it gets really tricky when you get down to the smaller planets. But then you have TRAPPIST-1 system, for example. That one's really tough, but it was very interesting. So people still devoted a lot of observing effort to try to measure masses. And I actually have to be honest, I don't remember if they managed to measure those masses or not, but they were pretty certain they were rocky planets, so they must have measured masses.
They did.
They did?
Yeah, TRAPPIST-1 is nice example because what it has gravitational configuration between planets.
Right.
So you can do it from transits.
Right. So this is probably this is too much. It could be. So some of these diamonds, they're not circles, the diamonds, because those masses will determine to transit timing variations. Yes, that's a good. So multi-planet systems, those are easiest to determine masses because sometimes you're going to have transit arriving earlier than expected, sometimes later than expected, and that's caused by the gravity of the additional planets in the system. So.
But can you see also in your system of what that 7 planets?
Yes.
Yes. You see also that one.
Yeah. So we have.
From your spectroscopic masses.
That's exactly what it is. Yeah. So we have results for just radial velocity, results just for TTP, and results using both.
Okay.
And then the ones that are both are the most precise. Yeah.
So 1 meter per second precision in radial velocity is that good enough? You're not walking on the edge of possibility.
Good enough for sub-Neptune and super-Earths. Those are our targets that we focus on. If we wanted to discover an Earth-like planet around a sun-like star, we would need 10 centimeters per second, right? So we can't reach that far. But for our statistical survey, where the goal was measure a large number of planets, let's focus on smaller sub-Neptune types of planets. 1 meter per second will still be sufficient.
There's still plenty of science to do even with
Oh, definitely, yeah, because they're large numbers, right? And it's possible to do large numbers thanks to TESS, because it found so many planets around bright stars, unlike Kepler. Kepler found same number of planets, but around faint stars, because it was staring at the same type of sky. And TESS was looking at the whole sky.
And also, I mean, a very nice advantage is very definite relation. I think because if you go back 10 years in papers, they will say, well, it's small, the Jupiter does not have a definite asteroid distribution. That was kind of knowledge that they had.
Well, it actually turns out that it's unreliable what the mass is at Jupiter size, above Jupiter sizes.
Right.
Because, yeah, you can have 10 Jupiters or 1 Jupiter size and they're equally sized planets.
So do you use 60 as your preferred limit, 60 Jupiter masses of the limit between planets or stars? 60.
No, so for something to be defined as a planet, it has to be below 13.
Okay, because of different variants.
Right, yeah. If it's above 13, people say, well, there might be some sporadic fusion of deuterium and you have a brown dwarf. So we stick with 13. But it's funny sometimes you go to NASA Exoplanet archive and it shows old and firm planets, you sort by mass, and you're going to see some planets of 26 Jupiter masses. Why is that in there?
If you go to Exoplanet, it goes all the way to 60 because we want to be consistent between the methods.
Yeah, to avoid losing them. But sometimes you might even discover it's a high mass, and later on it turns out it's lower mass, and it also depends on models and stars, so many variables. Let's just keep them according to NASA Exoplanet.
So you mentioned the 2 main theories for mass loss of planets, so photo evaporation and core heating.
So radius loss. The mass is pretty much the same. If you just lose atmosphere of Earth, for example, mass is pretty much going to stay the same, but radius can shrink.
Right. So you don't say so. I mean, you don't think that the mass changes substantially because of this, right?
Mostly radius, yes.
Yeah, okay. So then is it clear like which theory is more probable or more important?
Yeah, so there is consensus that photon evaporation is the most likely case. But there are some situations where there's no way that it's photon evaporation doing it because the star is so faint or the planet is so far. So there must be something else, at least in some cases, also doing it. And now with known masses, it's easier to bring this forward.
So it's probably sort of.
Probably.
Towards the beginning of the on Piper, and I noticed slight increase before and after the
Oh, I
then
think
the
you're
edge
talking
of
about Vatten, right? I think.
no, a bit further back.
Well, there's one light curve here.
That's a bit more back.
More back, there's no light curve. So there was one light curve I showed here in the Vatten stage, that one. Here.
Yeah, exactly. On this one, right?
So this, yes, I think you mean this one.
Yeah.
So I think this is different models on how they fit planets, and you pick the one that gives you the right one. So sometimes it's more aggressive, sometimes less aggressive. When they try to, it's called spark pipeline. Spark pipeline removes stellar variability, and sometimes it's rough to make it look nice, sometimes it's less rough. I think that's what that is. But
What's on the vertical axis? Flux?
this is flux, and this is orbital phase.
Right, just before the main transit.
So I also guess it could just be
So this is not, no, this is not astrophysical. This is just data reduction.
Do you do this part of vetting manually or?
This part of just opening this PDF and stare at it for a minute, that part is done manually.
Okay, and do you think that you could develop machine learning that?
Oh yeah, you could make this quicker. But I think this was also a great exercise for students. I was actually leading a small battalion of PhD students, and I taught them how to do all these things. So then we split targets. I'll do those 100, you do the next 100, and so on. So I think it was good learning exercise. This actually turns out to be one of the simplest parts of our survey. The hard part is gathering all the data and analyzing those and doing the systematics. But looking at PDF, this PDF is produced by the TESS mission. Every star that has a TESS planet candidate, it has this associated data validation report. Just super handy.
But what's the range of metallicities of host stars?
There's a paper, there's a picture, I might be able to, I have no idea.
I'll check if there's a paper.
And this is gonna be, yeah, one of the papers, just Google it. Yeah, so one of our science cases is this relationships between stellar parameters and planet parameters. Here, planets are correlations. So this is going to be one paper doing these kind of things. And we already know some correlations. We know that only stars with high metallicities can produce Jupiter-sized planets. So the first order, right? It's hard to have low metallicity star, but also have a large planet. So relationships like that.
It's a popular topic in stellar spectroscopy communities.
Yeah.
We let's see a kind of complete survey of bright stars, okay? So what are
What stars?
of bright stars, okay? So which distances are we talking about? I mean, for example, the Trappist one is, if I'm not mistaken, some 12 or 13 parsec away. Or can be more candidate or confirmed planets, and what is roughly the range of distances?
Of these? Don't know off the top of my head.
Local.
Yes, definitely. I mean, by clipping a 13B magnitude, that means it must be local stuff. Other than evolved planet systems, those can be further out. But other science cases, local, yes. Typically further out than Trappist one. That's really close, but still super faint. 16B magnitude. It's a red star, but still, that's really dark, even for being so close. Yeah, radio velocities are hard. You need a lot of signal to noise for these kind of meter per second precision. And just to point out, HIRIS is not one of the most precise spectrographs anymore. It used to be decades ago, but that's the one we could get a lot of observing time. And during our survey, there's a new instrument that came online with Keck 1, and it's called Keck Planet Finder, KPN. In fact, principal investigator is the same guy that's leading our survey, Andrew Howard. So outside of our TESS-Keck mission, we now started using KPF for some of the specific science cases, but that's outside of our survey. And at Gemini, we also have Močnik, which can go down to 30 centimeters per second. That's way more precise than HIRIS. But there's no way we could get that amount of observing time at Močnik. There's no way. We could get maybe 100 hours or so. We needed 300 nights. So.
Metallicity goes from minus 0.3 to 0.4.
There you go, around.
There are quite a lot of systems with around 0.4. Plus 0.4.
Which paper
Or
is that?
0.35. That's number 15.
15 parameters, I suppose.
Precise properties of 108 test planets and their hosts.
First we had that one, and then we added masses on.
There may be others, just one I opened.
Cool, well, thank you for that. Any last questions? Not, there's one more quick invitation at the end for a thing called Shadow the Scientist. It's a program that's ran by University of California, Santa Cruz, where people just log in over Zoom and see how people use their data or do observations at Subaru or wherever. And Gemini is a big partner in this. So we have universities, we have high schools who connect to our nighttime control room and see how observing looks like. And there's going to be people who explain what's going on, how we keep track of weather, what we're observing, what science is going on. So if you're interested, feel free to go to this webpage. There are recorded YouTube videos of past sessions, or you can just connect to some of the upcoming ones. We can make a dedicated session to organize just specifically for you if you have some students that might be interested to see how observing looks like. And it's great because that's your daytime when it's nighttime for us. So you can do it during classroom sessions. Anyway, just something to think about if you're interested.
That's really a great idea. The only part is that then you have to behave yourself.
Oh, you can turn, yeah, we have to behave ourselves, yeah. You can always turn off the camera. Yeah, sometimes we have many hundreds of people. I think our record is 700 attendance on a session, so be careful what you say. Well, I hope you found that interesting or enjoyable. And thank you all for listening.